Imagine you ask an AI system to fix, like a really complex, deeply buried bug in your company's code base.
Yeah.
It doesn't just print out some probable guess based on, a static data set of old code.
Right, which is what we're used to.
Exactly.
Yeah.
Instead, it secretly writes 5 different solutions in the background.
Yeah.
It spins up a virtual testing environment. It literally watches 4 of those solutions crash, analyzes the error logs, patches the 5th one, runs a final unit test to verify it, and then replies to you with a guaranteed fix.
Yeah, that's a whole different level.
You didn't just query a chatbot. You effectively just hired and managed a virtual engineering team.
And that shift, moving from a single static text generation to this dynamic iterative process that is the frontier we are crossing right now. It's the leap from passive language models to autonomous agents. And it honestly completely rewrites the architecture of artificial intelligence.
Welcome to the Deep Dives. Today, we're grounding our entire discussion in a massive, state-of-the-art overview from the Generative AI State-of-the-Art Foundation series. We are tearing into a landmark paper, and it's titled Agentic Reasoning for Large Language Models.
And the roster of institutions on this paper is, well, it's basically the Avengers of AI research.
Seriously, we're talking UIUC, Meta, Amazon, Google DeepMind, UCSD, and Yale.
Yeah, it is just a phenomenal synthesis of the field because, the researchers took hundreds of isolated breakthroughs like models playing video games, models writing software, models browsing the live web, and they mapped all of them onto a single unified architectural roadmap.
Right, and our mission for you today is to bypass all that dense academic formatting and unpack the actual mechanics of this transition. We'll explore the 3 distinct layers of agentic reasoning. So that's foundational agents, self-evolving agents, and collective multi-agent systems.
Which sounds like a lot, but we'll break it down.
We will. By the end of this deep dive, you'll grasp exactly how these architectures operate under the hood, and really why your relationship with your computer is about to change forever. Okay, let's unpack this. Before we get to, multi-agent swarms writing their own software updates, we need to establish the baseline.
Definitely.
We have to define what fundamentally separates an agent from the standard language model you're probably used to using every day.
Well, the contrast fundamentally comes down to computation over time. Traditional language model reasoning is what the researchers call a single pass through a context window.
A single pass, meaning it just reads and writes once.
Exactly. You provide a prompt, the model pushes that prompt through its neural network layers exactly one time, and it generates tokens until it hits a stop sequence.
Right.
So if it makes a logical error at, say, token number 10, it is stuck with that error for the remainder of the generation. It has literally no internal mechanism to pause, reflect, or course correct before you see the output.
It's just flying blind after that mistake.
Pretty much. But agentic reasoning alters that architecture to be interactive, dynamic, and stateful.
And the researchers formalized this through a framework they call the latent space view, which, instead of just mapping an input directly to an output, the system is designed around this think-act structure.
Yeah, the think-act separation is the mechanical core of an agent. A traditional model's thinking and its generation of the final output are the exact same process. There's no gap.
Right.
But the latent space view introduces a dedicated buffer for internal reasoning. The model generates a latent plan. It might even verbalize it as a hidden chain of thought that the user never actually sees.
Like an inner monologue.
Exactly. It evaluates that plan, and only then does it execute an action in the external environment.
I picture this as sort of the difference between consulting a massive encyclopedia and hiring an intern. With an encyclopedia, you look up a query, and it just statically provides whatever text is printed on the page.
Right, it's just retrieval.
But an agent operates like an intern. You assign them a goal, and they sit at their desk to draft a plan. They walk over to the filing cabinet, pull a document, realize, oh wait, this is from the wrong year, put it back, grab the correct one, synthesize the notes, and then they walk into your office with a finalized answer.
They are maintaining state, exploring, making mistakes, and adjusting. What's fascinating here is the underlying shift in how the industry scales intelligence.
What do you mean by that?
Well, for years, the brute force approach was scaling test time computation, meaning just pouring more compute into larger parameter counts so that single pass is more accurate.
Just making the brain bigger, basically.
Right. But now, the paradigm is scaling test time interaction. The architecture is explicitly designed to let the model spend compute on exploring different paths, interacting with tools, and adjusting its trajectory based on environmental feedback.
So if our AI intern is now capable of exploring and adjusting, how exactly does it navigate a really complex problem without just getting lost in the weeds?
That's a great question.
And that brings us to the first layer of the paper, which is foundational agentic reasoning. The architecture relies on three pillars: planning, tool use, and search. Let's start with planning, because this goes way beyond generating a basic to-do list, right?
Oh, absolutely. Planning in this context actually means mathematically simulating potential futures. The research highlights the integration of tree search algorithms directly into the language model's reasoning.
Okay, tree search.
Yeah, we're talking about algorithms like Monte Carlo tree search or MCTS and A-star search.
Let's define those for a second, because MCPS is the exact same backbone that allowed that AlphaGo system to beat human champions at the game of Go a few years back, right?
It is the exact same underlying logic. MCTS operates totally differently than standard generation. It doesn't just guess the next move.
Right.
It builds a branching mathematical tree of possible future moves. So in an agentic LLM, when it's faced with a complex logic puzzle, it generates multiple possible branches of thought.
Like drafting different outlines for an essay.
Exactly. And then it uses heuristic evaluators, which are essentially internal scoring functions, to simulate which reasoning path is most likely to yield a correct answer. It weighs the branches, prunes the logical dead ends, and commits compute only to the highest scoring path.
So it is literally calculating the probability of its own thoughts succeeding. That's wild. And to keep those thoughts organized over long horizons, agents use something called process formalization, right?
Yes, process formalization is key. They basically translate messy, ambiguous natural language into highly structured, code-like artifacts.
To keep themselves on track.
Right. Sometimes they use formal logic languages like PDDL, planning domain definition language, to basically lock their plan into an executable scaffold so they don't hallucinate halfway through the task.
Okay, so once that scaffold is built, the agent has to actually interact with the world to execute it. And this is where the second pillar, tool use, completely shatters the boundaries of the model.
Oh yeah, because a standard language model is walled off. It is terrible at precise arithmetic, and it's totally blind to real-time events.
Right, doesn't know what time it is. But tool use bridges that gap using frameworks like React, which stands for reasoning plus acting.
Exactly. This is where our intern actually pulls out a calculator or opens a web browser. The agent interleaves its hidden chain of thought with executable tool calls.
So its internal monologue might dictate, to calculate the current market cap of this company, I first need today's livestock price.
Yep. And then it generates a specific JSON payload to trigger a financial API. It waits for the server response, reads the real-time price, and injects that live data right back into its reasoning chain to finish the math.
And the scope of these tools is just expanding so rapidly. Look at a benchmark detailed in the paper called SWH, which evaluates software engineering agents.
That one is incredible.
Yeah, these agents aren't just auto-completing lines of code in a text editor. They're given a high-level GitHub issue, and they independently navigate massive, complex code repositories.
They use terminal commands to search directories.
Right, they run Python scripts to test their assumptions, they read the stack traces when their tests fail, and they iteratively modify the code base. I mean, they operate the exact same tool chain a human developer relies on.
Which brings us to the third pillar search, specifically Agentic RAG.
Now, we all know standard RAG, retrieval augmented generation. You chunk a document, embed it, and retrieve the top results based on vector similarity. It's a great baseline, but it's totally static.
Very static. You ask a question, it fetches 5 paragraphs, and it tries to synthesize them. But Agentic RAG fundamentally changes that dynamic.
How so?
Well, standard RAG is a one-shot fetch. Agentic RAG is an iterative investigation. The agent actively monitors its own knowledge gaps. It decides when to trigger a retrieval, what specific search string to formulate, and crucially, how to evaluate the payload it gets back.
Oh, so it double-checks its own search results.
Exactly. If the retrieved documents are irrelevant or contradictory, the agent critiques its own query, adjusts the search parameters, and triggers a new search, completely autonomously before it ever responds to the user.
Okay, I have to push back on this a little bit, though. If we are just wrapping a standard language model in a Python script that forces it to run Monte Carlo tree search, or we're just prompting it with a rigid React workflow, is the model actually reasoning? Or are we just stringing together clever prompts to make a statistical parrot look like it's thinking?
That is a very valid question, and it's a vital distinction. The researchers address it by separating two optimization modes. There's in-context reasoning versus post-training reasoning.
Okay, break that down for me.
What you just described, bolting on a workflow or using a structured prompt to guide the AI, is in-context reasoning. You take a frozen, pre-trained model, and you orchestrate its behavior entirely through clever prompting and external scaffolding.
So it's kind of a temporary fix.
It is a temporary external bandage, but the real breakthrough outlined here is post-training reasoning.
So the actual neural weights of the model are changing.
The neural fabric itself is shifting. Researchers are utilizing reinforcement learning algorithms, specifically methods like PPO, proximal policy optimization, or GRPO.
Right, PPO and GRPO.
These algorithms act as a highly tuned mathematical reward system. So instead of just showing the model static examples of correct answers, they let the model attempt a complex task in an environment.
Okay.
If the model successfully uses a tool or successfully backtracks from a dead end, the RL algorithm gives it a mathematical reward, slightly adjusting the weights to reinforce that specific behavioral pathway.
Oh, wow. So over millions of iterations, the capacity to plan, use tools, and backtrack becomes intrinsically baked into the model.
Exactly. It's no longer following an external prompt template. The reasoning strategies are native to the model.
That is basically the difference between giving someone a strict instruction manual to follow step by step versus them actually mastering the underlying skill.
Exactly.
But even with mastery, we eventually hit a wall. What happens when our foundational agent encounters a totally novel problem, tries its absolute best, and fails? If it just resets and makes the exact same mistake the next time we run it, it's not truly autonomous.
No, it's not.
That requires moving from a static agent to an evolving one.
And long-horizon autonomy demands self-improvement. The architecture for self-evolution relies on two interconnected mechanisms: feedback and memory.
Let's start with feedback.
Feedback operates in three distinct regimes. The first is reflective feedback, which happens during inference. Frameworks like reflection give the agent the ability to self-critique.
So it reviews its own work.
Yes. It drafts a response, reviews it against the original prompt, identifies logical leaps or unsupported claims, and revises its output before finalizing.
It's the AI having that moment of, wait, no, carrying the two here doesn't make sense, let me recalculate.
Precisely.
But that's just fixing a mistake in the moment. How does it learn permanently?
That requires the second type, parametric adaptation. When an agent discovers a highly successful reasoning trajectory, say, a novel weighted chain API calls together to solve a persistent bug, that trajectory is captured and used as training data.
Right.
The model is subsequently fine-tuned on its own successful outputs, permanently updating its weights so that the improved behavior is hard-coded for future runs.
Here's where it gets really interesting. The third type is validator-driven feedback. Think about a student taking a standardized math test on a computer. Every time they type the wrong answer, a harsh red buzzer goes off.
That's a stressful test.
Right.
Ugh.
The system doesn't tell the student why the answer is wrong or what the correct steps are, but that external binary signal success or failure forces the student to rethink their approach and try a different formula.
That's a great analogy. In an agentic system, that validator is often a rigid external environment, like a software compiler.
Right.
The agent writes a block of code and attempts to compile it. If it fails, the environment throws a stack trace error. The agent reads that error, hypothesizes what went wrong, adjusts the code, and recompiles.
It just keeps trying.
It will loop through this process, hypothesize, act, validate until the code compiles cleanly and the unit tests pass. It's a mechanism for ensuring absolute logical reliability without a human constantly supervising the output.
But feedback is utterly useless if you wake up with amnesia every morning.
Very true.
And that's where the second mechanism, memory, comes in. And we aren't just talking about, like, a flat text file of chat logs. The leap here is moving to structured memory.
Yeah, flat text is highly inefficient for complex retrieval over time. Frameworks like GraphRag transform how an agent stores its experiences. Instead of reading a transcript left to right, it builds a mathematical mind map.
How does that work in practice?
Well, if the agent learns a new fact about Tim Cook and his relationship to Apple, it doesn't just store the sentence. It creates a node for Tim Cook, a node for Apple, and draws a relational edge connecting them as CEO.
Okay, I see.
When the agent needs to recall corporate leadership structures later, it mathematically traverses those relational edges, allowing for massive, complex synthesis across disparate pieces of information.
And agents are actually learning how to manage that mind map themselves, right? It's called post-training memory control.
Exactly.
Think about how you learn. You don't blindly memorize every license plate you see on the highway. You categorize the important stuff, discard the noise, and consolidate the rest into long-term understanding.
That's exactly what systems like MemAgent do. They use reinforcement learning to autonomously decide what new data is valuable enough to write to the graph, and what outdated information should be purged to keep retrieval fast and accurate.
If we connect this to the bigger picture, pairing validator-driven feedback with structured memory creates what researchers call a meta-learning loop.
Yes.
The agent isn't just solving the immediate task, it is fundamentally optimizing its own problem-solving architecture over time.
The perfect example of this is a system called Voyager, which operates inside the Minecraft environment.
Oh, I love this example.
It doesn't just wander around breaking blocks, it literally writes its own executable code to create new skills.
Inside the game.
Inside the game. Let's say it realizes it needs to mine diamonds but doesn't know how. It synthesizes a JavaScript function to navigate deep underground and mine specific blocks. It runs the code in the simulation.
And what if it messes up?
If the avatar gets stuck in lava, the environment validator throws an error. Voyager reads the error, modifies the function to detect lava, tests it again, and succeeds.
Okay, but the critical step is what happens next, right?
Exactly. It takes that verified, successful code for safely mining diamonds and permanently commits it to a structured skill library in its memory.
Wow.
The next time it needs diamonds, it doesn't rewrite the code, it just calls the skill it previously mastered. It is permanently expanding its own capabilities without any human intervention.
It's basically writing its own software upgrades.
Yeah.
That is wild.
Yeah.
But let's push the boundary one step further. If a single self-improving tool-wielding agent is this capable, what happens when the objective is simply too massive for one instance to process?
You scale up.
Right. You can't just give one agent the prompt, build a Fortune 500 company. That brings us to the third layer of the roadmap, collective multi-agent reasoning. Welcome to the AI boardroom.
We are scaling up from isolated single-agent frameworks to multi-agent systems, or MAS. The driving philosophy here is the division of labor. Rather than forcing a single model to act as a jack of all trades, multiple specialized agents coordinate to achieve a unified, complex objective.
And you don't achieve that by just spinning up 10 identical clones and yelling go. You have to implement role differentiation.
Yep.
You assign them distinct personas and constraints.
Absolutely. The generic structure usually involves a leader or manager agent whose sole job is to take the massive human prompt and decompose it into a sequence of actionable subtasks.
Okay, so the manager delegates.
Then you have worker or executor agents who actually write the code, pull the financial reports, or query the databases. Finally, you have critic or evaluator agents who review the worker's output, run tests on it, and aggressively demand revisions if it doesn't meet the standard.
And those roles become highly specialized, depending on the domain, I'm guessing.
So, very specialized. In software engineering, you orchestrate architect agents, programmer agents, and dedicated QA tester agents. In quantitative finance, you pair a market analyst agent with a risk assessment agent to ensure aggressive trading strategies are checked against volatility metrics.
That's incredible.
But the breakthrough of multi-agent systems isn't just assigning titles, it's the architecture of their communication.
How so? Because they aren't just sending emails to each other.
No, not at all. In a standard computer network, communication is merely the transfer of data packets from point A to point B. But in agentic networks, communication is an extension of the reasoning process itself.
What does that look like mechanically?
One agent's external action literally serves as the environmental prompt that triggers the next agent's internal reasoning chain. When the critic agent outputs a message saying, "This function has a memory leak on line 42, that output isn't just text data.
Right.
It is the direct catalyst that forces the worker agent to spin up its MCTS algorithm and start simulating code patches.
So what does this all mean in practice? Because I have to ask the obvious question here. If you lock 3 large language models in a virtual room and tell them to solve a problem, doesn't that just create an infinite loop of hallucinations?
It definitely can.
Or worse, won't they just politely agree with each other's terrible ideas because they've been fine-tuned by humans to be helpful and agreeable?
That polite echo chamber is a heavily documented failure mode, actually. To combat it, the architecture relies on strict collaboration schemas and shared memory states.
Yep.
To prevent agents from just validating each other's hallucinations, they are programmed with explicit debate and conflict resolution protocols. They're given access to a centralized memory pool, a single source of ground truth regarding the environment.
So when the programmer says the code works and the QA tester says no, it doesn't, they can't just argue in circles. They have to actually prove it.
They're forced to show their work. The QA agent is required to present verifiable evidence, like the specific stack trace of a failed unit test or a contradictory retrieved document from the central database.
Wow.
The system is designed so that disagreements are resolved through empirical grounding rather than conversational persuasion, which forces the collective to achieve strict logical consistency.
But that raises an incredibly complex challenge, which the research identifies as the governance of agentic reasoning. When you have a decentralized swarm of autonomous agents spinning up their own subtasks, debating each other, writing code, and executing API calls at machine speed, how do you maintain oversight?
It's the billion-dollar question.
How do you ensure that the collective output of 1,000 micro-decisions remains aligned with the original human intent? Especially when the reasoning chain becomes so deep and convoluted that a human manager physically cannot read the entire transaction log.
This raises an important question, right? Trustworthiness in decentralized, high-speed agentic swarms is the defining open problem of this era. We are building systems that outpace our ability to audit them in real time.
Let's take a step back and look at the incredible journey we've just charted. We started with passive LLMs, models that essentially acted as powerful autocomplete engines stuck in a single passive computation. Then we moved to active solo agents that use tree search to plan, wield tools like calculators and search engines to interact with the world, and self-evolve through reflective feedback and structured graph memory.
And finally, we saw those agents scale into the AI boardroom, dividing labor, debating evidence, and executing massive objectives as a synchronized swarm. It is a profound structural evolution. Reasoning has migrated from a static internal calculation into a dynamic, distributed, and continuously adapting interaction with the real world.
For you, the listener, this fundamentally changes your relationship with the screen in front of you. You are no longer an interrogator trying to extract facts from a digital oracle. You are stepping into the role of a manager.
Exactly.
Your primary skill is no longer prompt engineering a clever sentence to trick an LLM into giving you the right answer. Your job is to delegate complex, ambiguous, long-horizon objectives to an autonomous team of agents, providing the high-level guardrails that keep them aligned.
You define the destination, and the multi-agent system constructs the map, builds the vehicle, and navigates the terrain.
Which leaves us with a final, slightly staggering thought to mull over. We've seen that these systems can autonomously generate their own subtasks. They can write their own code to synthesize new tools. They can critique their own logic, purge their own memory, and spin up specialized subteams to execute entirely novel workflows.
Yeah, they're doing the heavy lifting.
Right. If the agentic system is doing all the exploring, all the hypothesis testing, and all the synthesis, at what point does the human prompt actually become the bottleneck in the pursuit of scientific discovery?
It's a valid question.
Are we rapidly approaching a threshold where the machine no longer waits for us to formulate the right question because it's already busy discovering the answers we didn't even know we needed?
It forces us to reconsider the human role in the loop of innovation entirely.
It really does. Thank you so much for joining us on this deep dive into agentic reasoning. Keep questioning the systems beneath the surface, and remember, the next time you hit enter on a complex query, you might just be waking up an entire digital workforce.